Welcome to solverfy.
Okay, we need to talk about whether if we place a point charge here and an opposite point charge here, and we are somewhere in between them in a line with them, right, whether the electric field there is going to be equal to zero. And that whether, the electric field not in between them is going to be zero or not. So meaning if we're on one side of one of the point charges. Right, so we're assuming here that we're always in a line with the two charges, and we're assuming that they're of equal and opposite magnitude. So is it true that the electric field between them on that line will be zero? And I'll say no. I'll demonstrate why that is, and then we can put that in our own words, right? Okay, so recall that the electric field due to a point charge is K times the magnitude and sign of that charge, which I'll use Q for positive and negative Q for our negative, divided by the distance to that charge squared. Right? So the strength of this charge depends on the distance to it. Right? Meaning if we're really close to this charge, the electric field is stronger than if we're really far away from the charge. Right? So if I start here and I start walking to the right, the electric field I'm experiencing decreases over time. Okay. And the other thing to remember is that, well, for one, it decreases with the square of the distance, which means it drops off really rapidly. So just think of a simple thought experiment here. If I have a positive charge and then a million miles away, I have a negative point charge, right? And I'm standing right next to this positive point charge, which is going to feel stronger. The positive point charge, right? Because we're much closer to the positive point charge than we are from the negative point charge. And we said that the strength of that electric field decreases with the square of the distance to the point charge, right? So there's no way that they can have an equal effect on you, right? If the strength of the electric field is proportional to the distance to the point charge creating that electric field. Another way that you could put that mathematically is that you could say, if we said our distance, let's call this Q1, and we'll say our distance to Q1 is called R1. And that, so the electric field we experience due to 1 is K times Q1 over R1 squared. Well, let's say then that we call this charge 2. And so the electric field we experience due to charge 2 is K times Q2 over R1 squared, or R2 squared. Sorry. Okay. Now remember that the electric field you experience will be the sum of all electric fields you are experiencing due to the sum of all point charges nearby. Okay. So that means that the electric field total is going to be K times Q1. This is for anywhere in that line. K times Q1 over R1 squared plus K times Q2 squared, Q2 over R2 squared. Okay. Now we also know that Q1 is equal to negative Q2, right? They're opposite charges of equal magnitude. So we could also say that this is K times Q1 over R1 squared minus K times Q1 squared over R2 squared. Okay. Well, when will this equation equal 0? When will K times Q1 minus K times Q1 over R2 squared equal 0? Well, we can factor something out here. We can say K times Q1, right? We factor out the K times Q1. We're left with 1 over r1 squared minus 1 over r2 squared. Okay, if we set this equal to 0, right, this is going to be equal to 0 when k times q1 is 0, or when 1 over r1 squared minus r2 squared is equal to 0. Right, well, k times q1 is never going to be 0, right, because we know that it has a charge, so q is not 0. K is a constant. It's never going to be 0. So this doesn't matter. It's only going to be 0, or the net electric field is only going to be 0 when R1 equals R2. So E can only be 0 when R1 equals R2. If you're in a line with the 2 point charges, that's just how this works, right? So in your own words, you could say, because E is proportional to the distance between the point you measure the field at filed field, and a point charge two opposite and equal magnitude charges can only be zero. So I should say the charge, the field due to. The field due to. The field due to two opposite and equal magnitude charges can only be 0 when the distance from the point you are measuring from and the point charges is equal, right? So that's like saying it's only 0 at the point that's directly at the middle point of them. You get closer to 1, then the effect of it is higher than the effect of the other one, and the balance gets thrown off, right? So because E is proportional to the distance between the point you measure the field at and the point charge, the field due to two opposite and equal magnitude charges can only be 0 when the distance from the point you're measuring at and the point charges is equal.